Hello, and welcome to Space for Sleep. A black hole is not an empty place, and it is not a cosmic hole in the ordinary sense of the word. It is a region where matter has been compressed so completely that gravity changes the structure of space and time around it. Past a boundary called the event horizon, every possible path points inward. Not only rockets, not only radio signals, not only light, but every future direction available to anything inside leads deeper. That is why black holes matter. They are not just dramatic objects for science fiction. They are real laboratories of extreme physics. They test general relativity in the strongest gravitational fields we can observe. They reveal how stars die, how galaxies grow, how matter behaves when it is heated to millions of degrees, and where our current theories begin to reach their limits. A star is staggeringly complicated. Layers of nuclear fusion, magnetic fields, convection, rotation, chemical composition, radiation pressure, and turbulent gas. A black hole, by contrast, can be described from the outside by only a few measurable properties: mass, spin, and electric charge, with charge expected to be essentially negligible for real astrophysical black holes. Everything else, the star that collapsed, the gas that fell in, the history of the matter that built it, is hidden behind the horizon. Physicists sometimes describe this with the phrase, no hair. A black hole keeps very little visible memory of what made it. And yet, that apparent simplicity creates some of the deepest questions in modern science. What actually replaces the singularity at the center, where general relativity stops giving a physical answer? What happens to information that crosses the horizon? How did the first supermassive black holes grow so quickly in the young universe? Why do the black holes at the centers of galaxies seem to grow together with the galaxies around them? And what can gravitational waves, X-ray light, radio images, and future space observatories tell us about objects that cannot be seen directly? To understand black holes properly, we have to move through several layers of the subject: the theory that predicted them, the stars that create them, the observations that prove they are real, the strange physics near the event horizon, and the open questions that still keep black holes at the center of modern astrophysics. The theoretical groundwork for black holes was laid more than 2 centuries before anyone seriously believed such objects could exist. In 1783, an English clergyman and natural philosopher named John Michell wrote a paper for the Royal Society describing what he called a dark star. Michell reasoned, using Newtonian gravity and a recently established finite speed of light, that if a star were sufficiently massive and sufficiently compact, its escape velocity, the speed needed for any object to break free of its gravitational pull, could exceed the speed of light itself. Light, Michell reasoned, would be unable to leave such a star. It would fall back, the same way a thrown ball falls back to Earth if it isn't thrown fast enough to escape. The star would be invisible, not because it emitted no light, but because the light it emitted could never reach a distant observer. This was an extraordinary insight for 1783, derived entirely from Newtonian mechanics, decades before anyone understood that light's behavior near such extreme gravity would actually require an entirely different theory of gravity to describe correctly. Michell's idea was largely forgotten for more than a century, partly because it had no observational consequence anyone could test, and partly because the wave theory of light, which became dominant in the 19th century, made the concept of light having an escape velocity seem like a category error. Waves, unlike thrown balls, weren't obviously subject to the same kind of ballistic reasoning. The modern theoretical foundation came from Albert Einstein's general theory of relativity, published in 1915. General relativity reconceived gravity not as a force acting between masses across empty space, but as the curvature of space-time itself caused by the presence of mass and energy. Massive objects don't pull on each other directly. They warp the geometry of the space and time around them, and other objects move along the straightest possible paths through that warped geometry, paths that, from our ordinary perspective, look like orbits and falling trajectories. Within months of Einstein publishing his field equations, a German physicist named Karl Schwarzschild, while serving on the Russian front during the First World War, found an exact mathematical solution to those equations for the simplest possible case: a single, non-rotating, electrically neutral mass in otherwise empty space. The Schwarzschild solution described how space-time would be curved around such a mass, and embedded within it was something deeply strange. At a specific distance from the center of the mass, a distance now called the Schwarzschild radius, the mathematics produced a kind of boundary where the equations seemed to break down entirely. Within that boundary, in Schwarzschild's solution, the roles of space and time appeared to reverse in a mathematically meaningful sense. Falling toward the center became as inevitable as moving forward in time is for us. Schwarzschild died of an autoimmune disease just months after submitting his paper, never knowing what his solution would eventually be understood to describe. For decades afterward, the strange mathematical boundary in his solution was widely regarded as a mathematical artifact, a quirk of the coordinate system used, not a physical reality. Einstein himself, in a 1939 paper, argued that such an object could never actually form in nature, that physical processes would prevent matter from ever becoming compact enough to reach this boundary. It is worth understanding why Einstein and many of his contemporaries were so resistant to the idea that such extreme objects could actually exist, because their skepticism wasn't simply conservatism, it reflected a reasonable expectation, given the physics understood at the time, that nature would always find some way to prevent matter from collapsing without limit. Stars are held up against the relentless inward pull of their own gravity by outward pressure, and physicists in the early 20th century had already identified several distinct mechanisms by which that pressure could be generated. An ordinary star like our Sun is supported by the thermal pressure generated through nuclear fusion in its core, the outward push of extremely hot gas balancing the inward pull of gravity. When a star's nuclear fuel is exhausted and that thermal pressure can no longer be sustained, a different kind of pressure can take over for sufficiently low-mass stars: electron degeneracy pressure, a purely quantum mechanical effect arising from the Pauli exclusion principle, which states that no two electrons can occupy precisely the same quantum state. This pressure, entirely independent of temperature, can support a stellar remnant called a white dwarf against further collapse, provided the remnant's mass doesn't exceed a critical threshold calculated by the Indian astrophysicist Subramanian Chandrasekhar in 1930, a limit of about 1.4 times the mass of our Sun, now known as the Chandrasekhar limit. For more massive remnants, even electron degeneracy pressure proves insufficient, and the collapse continues further, with electrons and protons being crushed together to form neutrons, releasing a burst of neutrinos and producing an object supported instead by neutron degeneracy pressure, a similar quantum mechanical effect, but involving neutrons rather than electrons, and capable of supporting considerably more mass before failing, since neutrons are far more massive than electrons and the relevant quantum mechanical pressure scales accordingly. Such an object, a neutron star, is extraordinarily compact, typically only about 20 kilometers across despite containing more mass than our Sun, with a density so extreme that a single sugar cube-sized piece of neutron star material would weigh roughly as much as a mountain on Earth. But even neutron degeneracy pressure has its limits. Theoretical work in the 1930s by Oppenheimer and others, building on calculations by Lev Landau and Richard Tolman among others, established that neutron stars too have a maximum possible mass, beyond which neutron degeneracy pressure can no longer hold off gravitational collapse, a limit somewhere in the vicinity of 2 to 3 times the mass of our Sun. Though the precise value depends on details of nuclear physics at extreme densities that remain incompletely understood even today, since no laboratory on Earth can recreate conditions of comparable density and pressure. For a collapsing stellar core exceeding this limit, calculation after calculation by Oppenheimer and Snyder in 1939 and by every subsequent, more sophisticated analysis performed since, arrived at the same conclusion. There is no known force, no known type of pressure capable of halting the collapse. The star simply continues compressing without any natural stopping point that known physics can identify. The turning point came from understanding what happens to massive stars at the end of their lives. In 1939, the physicists J. Robert Oppenheimer and Hartland Snyder published a paper modeling the gravitational collapse of a massive star after it exhausts its nuclear fuel. Their calculations showed that for a sufficiently massive star, no known force, not the pressure of a normal gas, not the quantum mechanical pressure that supports white dwarfs, not even the more exotic pressure that supports neutron stars, could halt the collapse. The star would continue contracting, in principle without limit, crushing itself down past the point where any known physics could stop it. This was the theoretical birth of the black hole as a physically plausible object rather than a mathematical curiosity. But the idea remained on the fringes of physics for another 2 decades, overshadowed by the Second World War, the subsequent focus on nuclear physics, and a general scientific skepticism about whether such extreme objects could really exist in nature. It wasn't until the 1960s, with the discovery of pulsars, the development of more powerful mathematical tools for handling general relativity, and a new generation of physicists including John Wheeler, Roger Penrose, and Stephen Hawking, that the modern theory of black holes truly developed. It was Wheeler, in 1967, who popularized the term black hole itself, replacing more cumbersome earlier terms like gravitationally completely collapsed object, and the new name caught on immediately, capturing something essential about the object's nature in 2 simple words. So what, precisely, is a black hole? Let's build the concept up carefully, because the popular image, a kind of cosmic drain or vacuum cleaner, sucking in everything nearby, is misleading in important ways. A black hole is a region of space-time where gravity is so intense that nothing, including light, can escape from within a certain boundary once it has crossed that boundary. The boundary itself is called the event horizon. It is not a physical surface in the way the surface of a star or planet is physical. There's no material structure there, nothing you could touch or that would resist a spacecraft passing through it. It is, instead, a mathematical boundary in space-time, the point of no return, the surface beyond which the curvature of space-time becomes so extreme that all possible paths, every direction you could possibly travel, even at the speed of light, lead inward, toward the center, rather than outward, away from it. This is the crucial conceptual leap that's often missed in popular explanations. Inside the event horizon, inward isn't a direction you can choose to avoid by moving fast enough or maneuvering cleverly. It's not like being in a strong current that you might swim against if you're strong enough. Once you're inside the event horizon, moving toward the center is as unavoidable as moving forward in time is for you right now, lying there listening to this. You cannot choose not to move forward in time. Inside a black hole's event horizon, you cannot choose not to move toward the center. The geometry of space-time itself has been so thoroughly bent that the future, for anything inside, simply points inward. The size of the event horizon, the Schwarzschild radius, for a non-rotating black hole, depends directly and simply on the mass of the black hole. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. For a black hole with Earth's mass, something that doesn't exist in nature, since Earth lacks the mass needed to ever collapse into a black hole through any known process. But useful as a thought experiment, the radius would be less than a centimeter, about the size of a marble. The more massive the black hole, the larger its event horizon, and the relationship is linear: double the mass, and you double the radius. This means something counterintuitive. Very massive black holes are actually less dense, in an average sense, than smaller ones. The supermassive black hole at the center of the galaxy M87, with a mass of about 6.5 billion times that of our Sun, has an event horizon roughly the size of our entire solar system, and the average density of matter within that enormous volume. If you imagine the black hole's mass spread evenly through the volume defined by its event horizon, would actually be lower than the density of air. The intensity of the gravitational effects at the event horizon, what's called the tidal force, the difference in gravitational pull between your head and your feet if you were falling in, is actually gentler for very large black holes than for small ones, because the curvature of spacetime is more gradual when spread over a larger radius. This has a genuinely strange consequence. For a sufficiently massive black hole, you could, in principle, cross the event horizon without immediately feeling anything unusual at all. There would be no dramatic boundary crossing, no sudden change in sensation. You would simply be moving through space as you always had, except that, unknown to you in the moment, you would have just passed the point beyond which return to the rest of the universe is no longer physically possible, no matter what you did, no matter how powerful your engines, no matter how clever your plan. At the center of a black hole lies the singularity, the point, in the simplest non-rotating case, where the curvature of spacetime becomes infinite, where the equations of general relativity stop producing any meaningful prediction at all. This is widely understood, even among the physicists who study black holes most closely, to represent a breakdown of the theory rather than a literal description of physical reality. General relativity is an extraordinarily successful theory, but it is a classical theory. It doesn't incorporate the principles of quantum mechanics, which become essential at very small scales and very high densities. Most physicists believe that a complete theory of quantum gravity, something that successfully merges general relativity with quantum mechanics, a goal that has eluded physics for nearly a century, would replace the singularity with something else, perhaps an extremely dense but finite region, perhaps something stranger still, structured by physics we don't yet have the tools to describe. There are, broadly, several categories of black holes that astronomers have identified, distinguished primarily by mass and by the processes that form them. Stellar mass black holes form from the collapse of massive stars at the end of their lives. When a star with sufficient mass, generally more than about 20 times the mass of our Sun, though the exact threshold depends on details of the star's composition and evolutionary history, exhausts the nuclear fuel in its core, it can no longer generate the outward pressure needed to balance the inward pull of its own gravity. The core collapses catastrophically, in a fraction of a second, while the outer layers of the star are blown outward in a supernova explosion of extraordinary violence and brightness, briefly outshining entire galaxies. If the collapsing core retains enough mass after the explosion, and the precise threshold is still debated among astrophysicists, somewhere in the range of 2 to 3 times the Sun's mass, no known force can halt the collapse, and a black hole forms. Stellar mass black holes detected through various methods typically range from about 5 to perhaps 100 times the mass of our Sun, with the discovery of gravitational waves in 2015 revealing populations of black holes at the higher end of this range that were not well predicted by earlier models based on X-ray observations alone. Supermassive black holes are an entirely different category, with masses ranging from hundreds of thousands to tens of billions of times the mass of our Sun. These reside at the centers of essentially all large galaxies, including our own Milky Way, which hosts a supermassive black hole called Sagittarius A star with a mass of about 4 million times that of our Sun. The formation mechanism for supermassive black holes is one of the genuinely unresolved questions in astrophysics, which we will return to in detail later. The simplest models, involving the merger and accretion growth of stellar mass black hole seeds over cosmic time, struggle to explain how some supermassive black holes appear to have grown so large so quickly in the early universe, within the first billion years after the Big Bang. Intermediate mass black holes, with masses between roughly 100 and 100,000 times the Sun's mass, occupy a category that for decades was almost entirely theoretical, predicted to exist as a kind of evolutionary stepping stone between stellar mass and supermassive black holes, but extremely difficult to detect because they don't fit neatly into the observational signatures that reveal either smaller or larger black holes. In recent years, increasingly compelling candidates have been identified, including through gravitational wave detections of black hole mergers that produced remnants in this intermediate mass range, and through more indirect observations of unusually luminous X-ray sources in other galaxies that may represent intermediate mass black holes actively accreting material. There is another way to classify black holes that is sometimes more useful than simply listing their masses, by asking whether they are quiet or active. A quiet black hole may reveal itself only through gravity. It may sit in a binary system with an ordinary star, tugging that star into a slow wobble that precise instruments can detect. It may drift through interstellar space almost invisibly, leaving no bright accretion disk, no jet, no obvious radiation. Most black holes in the universe may be like this, not theatrical, not glowing, not devouring anything at a visible rate, simply present as dark compact masses. An active black hole is different. Give a black hole a supply of gas, and the black hole's environment becomes one of the brightest engines in the cosmos. The black hole itself remains dark, but the matter falling toward it forms an accretion disk, heats through friction and compression, and radiates with extraordinary intensity before crossing the horizon. This is the important distinction. We never see the black hole directly. We see the matter losing energy as it approaches the black hole, and we see the way gravity bends and shapes that light. This is why the same kind of object can look completely different depending on its surroundings. A stellar mass black hole in an empty region of space might be almost impossible to find. The same mass black hole in a close binary system can become an X-ray source. A supermassive black hole with little gas nearby, like Sagittarius A star at the center of the Milky Way, can be comparatively dim. A similar black hole in a gas-rich young galaxy can become a quasar visible across most of the observable universe. The black hole is not the whole story. The environment decides whether the black hole is silent or blazing. There is also a more speculative category, primordial black holes, which would not have formed from the collapse of stars at all, but rather from extreme density fluctuations in the very early universe, within the first fraction of a second after the Big Bang, before any stars existed. If they exist, primordial black holes could span an enormous range of masses, from microscopic, potentially smaller than an atom, though carrying the mass of a mountain, to substantial fractions of a solar mass. Primordial black holes have been proposed as a possible explanation for dark matter, the mysterious substance that appears to constitute about 85% of all matter in the universe, but that has never been directly detected through any means other than its gravitational effects. The primordial black hole dark matter hypothesis remains a minority position among physicists, constrained increasingly tightly by observational searches that have ruled out primordial black holes as the dominant component of dark matter across most of the plausible mass range. though some narrow windows of mass remain observationally unconstrained and scientifically interesting. It's worth dwelling a little longer on each of these categories, because the differences between them are not merely about mass. They reflect entirely different formation histories, entirely different astrophysical environments, and entirely different observational signatures. Stellar mass black holes are, relatively speaking, the best understood category because their formation pathway connects directly to well-studied stellar physics. The life of a massive star follows a predictable arc. It fuses hydrogen into helium in its core for millions of years. Then, as hydrogen is exhausted, begins fusing progressively heavier elements, helium into carbon, carbon into oxygen, and so on, up through silicon fusing into iron, in a series of increasingly rapid burning stages, each one shorter than the last, with the final stage of silicon burning lasting only about a day before the core, now mostly iron, can no longer generate energy through fusion at all, because iron fusion actually absorbs energy rather than releasing it. At that point, the core's only support against gravity disappears almost instantaneously, and it collapses in well under a second, triggering the supernova explosion that disperses the star's outer layers while the core itself, if massive enough, continues collapsing into a black hole. The boundary between stellar remnants that become neutron stars and those that become black holes is not perfectly sharp. It depends on the mass of the collapsing core after the supernova has stripped away the outer layers, and on details of the star's rotation, magnetic field, and even the specific nuclear physics governing how the core behaves in those final, violent moments. There is a range of masses, sometimes called the mass gap, between the most massive known neutron stars and the least massive known black holes, where astronomers have historically found relatively few confirmed objects, though gravitational wave observations in recent years have begun to populate this gap with intriguing candidate detections, raising new questions about whether the gap is a genuine feature of stellar collapse physics or simply a reflection of limited observational sensitivity in this particular mass range. There is also a particularly dramatic and theoretically distinct possible mechanism for stellar mass black hole formation, applicable to only the very most massive stars, direct collapse without an accompanying supernova at all. For especially massive progenitor stars, generally estimated above roughly 40 solar masses, though the precise threshold remains uncertain and depends sensitively on the star's composition and rotation. Some theoretical models suggest the core collapse can proceed so completely and so rapidly that the shock wave which would normally produce a visible supernova explosion fails to successfully propagate outward through the star's remaining layers, instead stalling and being reabsorbed, with the entire star's mass quietly collapsing directly into a black hole without ever producing the brilliant explosive display associated with ordinary supernovae. Indirect observational support for this failed supernova scenario came in 2017, when astronomers using the Large Binocular Telescope reported that a massive, luminous red supergiant star in a nearby galaxy, which had been under regular observation for years, simply vanished from view without any corresponding supernova explosion ever being detected. Exactly the signature predicted for a direct collapse event, in which a massive star's light would gradually and then abruptly disappear from view as it collapsed inward, with no explosive flash to mark the transition. Once a black hole forms, whether through an ordinary supernova-accompanied collapse or through this more exotic failed supernova mechanism, it does not necessarily remain isolated for the rest of cosmic time. Many of the most massive stars exist within binary or even more complex multiple star systems, and if both stars in a sufficiently massive binary eventually collapse into black holes, the resulting pair of black holes can remain gravitationally bound to one another, slowly spiraling closer together over enormous timescales as they very gradually lose orbital energy to the emission of gravitational waves. Extraordinarily faint at first, when the black holes are still widely separated, but growing dramatically stronger as the pair spirals closer together, finally culminating, after potentially billions of years of slow and spiral, in the catastrophic, rapid final merger that produces the kind of powerful, detectable gravitational wave signal that LIGO and Virgo have now observed on numerous occasions. Alternatively, in sufficiently dense stellar environments, particularly the crowded cores of globular star clusters, where stars and stellar remnants are packed together far more closely than in the relatively sparse environment of our own galaxy's outer regions, black holes that didn't originally form together can nonetheless gravitationally capture one another through close dynamical encounters, forming binary pairs through an entirely different formation channel than the evolution of an originally binary star system. Distinguishing between these different formation channels, binary stellar evolution versus dynamical capture in dense clusters, based on the detailed properties of detected gravitational wave signals, particularly the alignment or misalignment of the merging black hole's spins relative to their orbital motion, has become an active and genuinely productive area of gravitational wave astrophysics research. Supermassive black holes, residing at the centers of galaxies, exist in an entirely different astrophysical context. Nearly every sufficiently large galaxy in the observable universe appears to host one, and there is a well-established, if not yet fully explained, correlation between the mass of the central black hole and the properties of the surrounding galaxy, particularly the mass of the galaxy's central bulge of stars. Galaxies with larger central bulges tend to host more massive central black holes, in a relationship called the M-sigma relation, which suggests that the growth of the black hole and the growth of the galaxy around it are not independent processes but are somehow coupled, regulating each other through the energetic feedback processes we'll discuss later. This relationship is one of the most important clues that supermassive black holes are not simply passive passengers sitting at galactic centers, but active participants in shaping the galaxies that contain them. Intermediate mass black holes occupy a category whose very existence, for decades, sat on uncertain observational ground. The challenge in confirming them is partly technical. Stellar mass black holes are most readily detected through their gravitational interaction with a closely orbiting companion star, a method that becomes increasingly difficult to apply as the black hole's mass grows large enough that suitable binary companions become rare, but not yet large enough to produce the dramatic, unmistakable signatures, the powerful jets, the extreme luminosity, that mark a supermassive black hole's presence at a galactic center. Some of the most compelling intermediate mass black hole candidates have come from a class of objects called ultraluminous X-ray sources, found in the outskirts of nearby galaxies, radiating X-rays at levels too bright to be easily explained by ordinary stellar mass black holes accreting at sustainable rates, suggesting either an intermediate mass black hole or some more exotic accretion physics still being worked out. The 2019 detection by LIGO and Virgo of a black hole merger producing a remnant of about 142 solar masses, squarely within the intermediate mass range, provided some of the most direct and unambiguous evidence, yet that black holes of this size genuinely exist in nature, even if their formation pathway and overall abundance throughout the universe remain considerably less well understood than for their stellar mass and supermassive cousins. How do we actually know black holes exist? This is worth dwelling on carefully, because for most of the history of the concept, black holes were purely theoretical, mathematically consistent, but with no direct observational confirmation. The evidence has accumulated gradually, through several independent lines of investigation, each adding weight to the conclusion that these objects are not just mathematically possible, but physically real and surprisingly common throughout the universe. The first compelling evidence came from X-ray astronomy. Black holes themselves emit no light. That is, after all, the defining characteristic of the event horizon. But matter falling into a black hole, particularly matter from a companion star in a binary system, doesn't fall in cleanly and quietly. As gas is pulled from the companion star by the black hole's gravity, it doesn't fall straight in. Instead, due to the conservation of angular momentum, it spirals inward, forming a flattened, swirling disk of material called an accretion disk. As the gas in this disk spirals closer to the event horizon, friction between adjacent layers of gas moving at different speeds heats the material to extraordinary temperatures, millions of degrees, hot enough that the gas emits intense X-ray radiation before it crosses the point of no return. This X-ray emission can be detected by telescopes in space, since Earth's atmosphere blocks X-rays from reaching ground-based observatories. The first strong candidate black hole identified this way was Cygnus X1, an X-ray source discovered in 1964 and identified as a likely black hole through the 1970s, based on measurements of its mass derived from its orbital interaction with a visible companion star. The mass, roughly 15 times that of our Sun, was too large to be a neutron star, the only other known extremely compact object, leaving a black hole as the most plausible explanation. Famously, Stephen Hawking made a wager with fellow physicist Kip Thorne in 1974, betting against the existence of a black hole in Cygnus X1, a bet that Hawking conceded in 1990 as the observational evidence became overwhelming, in a gesture that has become one of the more charming anecdotes in the history of physics. A second major line of evidence comes from the direct observation of stellar orbits around the center of our own galaxy. Beginning in the early 1990s, astronomers using increasingly powerful telescopes equipped with adaptive optics, technology that corrects in real time for the blurring effects of Earth's atmosphere, began tracking the precise motions of individual stars orbiting an invisible, compact object at the center of the Milky Way. Over more than 2 decades of patient observation, these stars were tracked through complete orbits, allowing astronomers to apply Kepler's laws of orbital motion, the same basic physics that describes planetary orbits around the Sun, to calculate the mass of the object the stars were orbiting. One particular star, designated S2, completes a full orbit around the galactic center in only about 16 years, passing at its closest approach within about 17 light hours of the central object, a distance comparable to the size of our own solar system, while moving at speeds reaching nearly 3% of the speed of light. The calculations derived from S2's orbit and from the orbits of several other closely tracked stars indicated an object with a mass of approximately 4 million times that of our Sun, concentrated within a region too small and too dark to be anything other than a black hole. This work, led by Reinhard Genzel and Andrea Ghez, earned them a share of the 2020 Nobel Prize in Physics. The third major line of evidence, and arguably the most dramatic confirmation in the history of the field, came in 2015 with the first direct detection of gravitational waves. Predicted by Einstein's general relativity a century earlier, gravitational waves are ripples in the fabric of space-time itself, generated by the acceleration of massive objects, with the most powerful sources being the violent mergers of extremely compact objects like black holes and neutron stars. These waves had never been directly detected, partly because the predicted effect, a tiny stretching and squeezing of space itself, was almost unimaginably small, requiring detectors of extraordinary sensitivity. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consists of 2 facilities in the United States, each using laser beams split and bounced down two perpendicular 4-kilometer-long vacuum tunnels to measure changes in distance with a precision smaller than 1/10,000th the width of a proton. On September 14, 2015, both LIGO detectors recorded an identical, characteristic signal, a rapid rise in frequency and amplitude over a fraction of a second, the unmistakable signature predicted for two massive compact objects spiraling together and merging. Detailed analysis determined the source, two black holes, with masses of about 36 and 29 times the mass of our Sun, merging into a single black hole of about 62 solar masses, releasing the equivalent of about 3 solar masses worth of energy as gravitational waves, in an event that occurred approximately 1.3 billion years ago, in a galaxy far beyond our own. This single detection confirmed not just the existence of gravitational waves, but the existence of stellar mass black holes with masses considerably larger than astronomers had typically expected based on X-ray observations of black holes in our own galaxy, opening an entirely new window onto the population of black holes throughout the universe. Since that first detection, LIGO and its sister observatory Virgo in Italy, joined more recently by CAGRA in Japan, have detected hundreds of gravitational wave events. By 2026, the LIGO Virgo CAGRA catalog had grown to hundreds of confirmed signals, including many black hole mergers. The result is no longer a single dramatic confirmation, but a statistical population, black holes of different masses, different spins, different merger histories, gradually revealing how often these objects form and collide across cosmic time. The technical achievement underlying these detections is itself worth pausing on, because the engineering required borders on the extraordinary. The distortion of space-time produced by even the most powerful black hole mergers, by the time the resulting gravitational wave has traveled hundreds of millions or billions of light years to reach Earth, stretches and compresses the 4-kilometer arms of LIGO's detectors by an amount smaller than 1/10,000th the diameter of a proton, a distortion so minute that achieving the sensitivity required to detect it meant developing entirely new categories of precision measurement technology, including mirror suspension systems isolated from seismic vibration to a degree previously unachieved, vacuum systems among the largest and most pristine ever constructed, and laser systems stable enough to measure such infinitesimal length changes reliably. The first detection in 2015 came only after decades of patient technological development, beginning with proposals in the 1970s and 1980s, through an initial, less sensitive generation of LIGO detectors that operated from 2002 to 2010 without a single confirmed detection, followed by a major upgrade to the current advanced LIGO configuration that finally achieved the sensitivity needed. As the catalog of detected mergers has grown into the hundreds, astronomers have begun to extract genuinely new astrophysical insights from the population as a whole, rather than from individual detections alone. The distribution of black hole masses found through gravitational wave detections shows interesting structure, including what appears to be a relative excess of black holes with masses clustered around specific values, possibly reflecting details of the stellar physics that determines exactly how much mass remains in a black hole after a star's core collapses and the resulting supernova strips away the outer layers. The detected merger rate, how frequently these events occur throughout the observable universe, has allowed astronomers to begin constraining models of how binary black hole systems form in the first place, whether predominantly through the evolution of binary star systems that remain gravitationally bound through both stars' violent deaths, or through dynamical processes in dense stellar environments like globular star clusters, where black holes can gravitationally capture each other through close encounters long after either one individually formed. In 2017, LIGO and Virgo achieved another landmark detection, not a black hole merger, but the merger of two neutron stars, an event designated GW 170817. Unlike black hole mergers, which produce gravitational waves but no electromagnetic radiation that conventional telescopes can detect, the neutron star merger was also observed across the entire electromagnetic spectrum, gamma rays, optical light, infrared, radio waves, by dozens of telescopes around the world that responded within hours to the gravitational wave alert. In a landmark demonstration of what astronomers call multi-messenger astronomy, the event confirmed that neutron star mergers are a significant source of heavy elements throughout the universe, including gold and platinum, produced through a rapid neutron capture process in the extraordinarily neutron-rich material ejected during the collision. While this particular event involved neutron stars rather than black holes, it demonstrated the broader scientific power of combining gravitational wave detection with traditional telescope observations, and similar multi-messenger campaigns are now a standard part of how astronomers respond to promising gravitational wave detections, including searches for any possible electromagnetic counterpart to black hole mergers, though none has yet been convincingly confirmed. The fourth and most visually striking line of evidence came in April 2019, when the Event Horizon Telescope collaboration released the first ever image of a black hole shadow, a dark central region surrounded by a glowing ring of superheated material, captured from the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The Event Horizon Telescope is not a single instrument, but a coordinated network of radio telescopes spread across the globe, from Hawaii to Spain to the South Pole, linked together using a technique called very long baseline interferometry to synthesize the resolving power of a telescope effectively the size of the entire Earth. The technical challenge involved in producing this image is worth appreciating in some detail. Resolving an object as small and angular size as a black hole's event horizon, even one as physically enormous as M87's, whose event horizon is roughly the size of our entire solar system, but which sits at such an immense distance that it subtends an angle in the sky comparable to viewing an orange on the surface of the moon from Earth, requires angular resolution far beyond what any single telescope, however large, could achieve. The solution, very long baseline interferometry, involves precisely synchronizing observations from telescopes scattered across continents, each equipped with extraordinarily precise atomic clocks to timestamp the incoming radio signals with nanosecond accuracy, and then combining the resulting data computationally after the fact to mathematically reconstruct an image as though it had been captured by a single telescope with a diameter equal to the maximum separation between the participating observatories, in this case, roughly the diameter of Earth itself. The data volume involved was staggering. Each telescope in the array recorded data at a rate of several gigabits per second over multiple nights of observation in April 2017, accumulating several petabytes of raw data in total, so much data that it was physically impractical to transmit it over the internet, and instead had to be flown on hard drives to central processing facilities. The South Pole Telescope's data, recorded during the Antarctic winter, couldn't even be retrieved until months later, when seasonal flights to the pole resumed. Processing this enormous dataset into a single, scientifically reliable image took nearly 2 years, involving multiple independent teams using different computational imaging techniques, specifically structured so that the final result wouldn't depend on the assumptions of any single algorithm or research group. A methodological precaution against the risk of the imaging process itself somehow producing a misleading, artifact-driven result rather than a genuine reflection of the data. The image that emerged, when finally unveiled to the public in a coordinated series of press conferences around the world in April 2019, showed exactly what general relativity predicted decades earlier: a dark, roughly circular shadow, the silhouette cast by the black hole's event horizon, and the additional light-bending effects of its surrounding gravity, surrounded by a bright, asymmetric ring of glowing plasma in the surrounding accretion disk. The asymmetry in the ring's brightness, brighter on one side than the other, was itself a predicted and scientifically meaningful feature, arising from relativistic beaming. Material on the side of the accretion disk rotating toward the observer appears brighter, due to relativistic effects that boost the apparent intensity of radiation from objects moving toward you at a significant fraction of the speed of light, while material rotating away appears correspondingly dimmer. This asymmetry allowed astronomers to determine not just the black hole's mass, found to be about 6.5 billion times that of our Sun, among the most massive black holes known, but also, with somewhat less precision, the direction of its rotation and the orientation of its accretion disk relative to Earth. In 2022, the same collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy, a more technically challenging target than M87's black hole, despite being much closer, because the rapid orbital timescales around our galaxy's smaller central black hole meant the material in its accretion disk was changing on timescales of minutes, requiring sophisticated techniques to produce a stable image from data collected over an extended observation period. The resulting image, again showing a dark central shadow surrounded by a glowing ring, matched theoretical predictions with remarkable precision, providing direct visual confirmation of the object whose presence had previously been inferred only indirectly, through the orbital motion of nearby stars. The Event Horizon Telescope images are also important for what they did not show. They did not show a solid surface. They did not show light escaping from inside the horizon. They showed a shadow whose size and shape matched the predictions of general relativity for a black hole with the measured mass. That agreement matters because the image was not merely a picture for the public. It was a measurement of space-time geometry in the strongest gravitational field ever resolved by a telescope. The ring is not the event horizon itself. It is light from hot plasma, bent by gravity into paths that curve around the black hole before some of that light finally escapes toward Earth. Some photons orbit the black hole more than once before leaving. Others are captured. The dark center is therefore not simply a black disk blocking light, but a combination of photon capture, gravitational lensing, and the absence of escaping radiation from the region beyond the horizon. This is why the word image can be slightly misleading. The EHT did not photograph a black hole the way a camera photographs the moon. It reconstructed radio waves collected by a planet-sized network of telescopes, then converted those measurements into a map of emission near the horizon. The result is still a real image, but it is an image created at the edge of what measurement can do. Together, these four lines of evidence: X-ray emission from accretion disks, the orbital dynamics of stars around galactic centers, the gravitational wave signatures of merging black holes, and direct imaging of event horizon shadows, represent an overwhelming, redundant confirmation that black holes are real, physical objects, not merely a mathematical curiosity within Einstein's equations. Let's turn to the question of what would actually happen to an object or a person in the kind of thought experiment that physicists use to build intuition, falling into a black hole. This is a topic where popular depictions in film and fiction often get the physics seriously wrong, and where the actual predicted physics is, in its own way, stranger than most fictional treatments. The experience of falling into a black hole depends enormously on the black hole's mass. For a stellar mass black hole, say, 10 times the mass of our Sun, the tidal forces become significant long before you reach the event horizon. Tidal force is simply the difference in gravitational pull between 2 points at different distances from the source. Your feet, if you're falling feet first, are closer to the black hole than your head, and therefore experience a stronger pull. For an ordinary planet like Earth, this difference is utterly negligible across the length of a human body. Near a stellar mass black hole, the difference becomes extreme. As you approach the event horizon, the gravitational pull on your feet would become so much stronger than the pull on your head that your body would be stretched, elongated along the direction of fall, and compressed from the sides, a process physicists have, with a certain dark humor, named spaghettification. Long before reaching the event horizon of a stellar mass black hole, an infalling human body would be torn apart at the molecular level by these tidal forces. For a supermassive black hole, the situation is dramatically different, as mentioned earlier. Because the event horizon is so much larger and the curvature of space-time at that boundary correspondingly more gradual, the tidal forces at the event horizon of a black hole, like Sagittarius A star or M87 central black hole, are far gentler, gentle enough that a falling human could cross the event horizon without being torn apart, and indeed without any local, immediately detectable sensation marking the crossing at all. It's worth being precise about why this is true, because the physics behind it is genuinely elegant. Tidal force scales with the mass of the black hole divided by the cube of the distance from its center. The event horizon's radius, meanwhile, scales linearly with mass. So as you compare black holes of increasing mass, the tidal force experienced at the event horizon itself, at a distance equal to the Schwarzschild radius, actually decreases because the radius is growing faster than the mass needs to grow to compensate. A 10 solar mass black hole has tidal forces at its event horizon strong enough to disintegrate a human body well before reaching the horizon. A black hole of a few 100,000 solar masses or more, well within the supermassive range, has tidal forces at its event horizon gentle enough that a human could, in principle, survive the crossing itself, only to be torn apart much later, deeper inside, as they continued falling toward the singularity and the tidal forces there grew correspondingly stronger. This means that for the supermassive black hole at the center of our own galaxy, an astronaut falling in would cross the event horizon, the boundary beyond which return is permanently, physically impossible, without any local indication that anything irreversible had just occurred. They would continue falling, watching their instruments, observing their surroundings, for a period of time afterward, calculated to be on the order of tens of seconds for Sagittarius A star's particular mass, before the increasingly extreme tidal forces near the singularity itself would finally become severe enough to be felt, and eventually fatal. This raises one of the most genuinely strange and frequently misunderstood aspects of black hole physics: the difference between what an infalling observer experiences and what a distant observer watching them sees. From the perspective of someone falling into a black hole, their own clock, their own experience of time passing, proceeds normally. They would fall through the event horizon, continuing toward the center, in what would feel to them like an ordinary, continuous passage of time, taking a finite and actually quite short amount of subjective time to reach the singularity, depending on the black hole's mass. For a supermassive black hole like Sagittarius A star, perhaps tens of seconds from event horizon to singularity. But from the perspective of a distant observer watching this fall, someone safely far away, watching through a telescope, the picture looks entirely different. As the falling object approaches the event horizon, the immense gravitational field causes time, as measured by the distant observer, to appear to slow down for the falling object, an effect called gravitational time dilation. The falling object appears to move more and more slowly as it approaches the horizon, its image becoming increasingly redshifted, its light stretched to longer and longer wavelengths by the same gravitational effects, until, in the limit, the falling object appears to freeze at the event horizon forever, its image growing dimmer and dimmer as the redshift increases, but never quite disappearing, never quite visibly crossing the boundary, according to the distant observer's clock. This is not a contradiction. It's one of the genuinely strange and well-established consequences of general relativity, a vivid illustration of the fact that time itself is not absolute, but depends on the observer's position within a gravitational field and their state of motion. Both descriptions, the falling observer who crosses the horizon in a finite, short time, and the distant observer who never quite sees them cross it, are correct within their respective frames of reference. There is no single, universal now that both observers share once gravity becomes this extreme. The mathematics of the Schwarzschild solution, when examined more carefully than Schwarzschild himself initially appreciated, actually contains additional structure beyond the simple picture of an event horizon and a singularity. When physicists in the mid-20th century worked out the complete, maximally extended version of the Schwarzschild geometry, a task largely completed by Martin Kruskal in 1960, using a coordinate system that properly handles the apparent singularity at the event horizon, which turns out to be merely an artifact of the original coordinate Schwarzschild used rather than a genuine physical singularity, they found that the full solution describes not just a black hole, but a black hole connected to a mirror image white hole, a hypothetical object from which matter and light could only ever emerge, never enter, joined together through a kind of bridge connecting two entirely separate regions of spacetime, sometimes called an Einstein-Rosen bridge, a precursor concept to what is more popularly known today as a wormhole. It's important to be clear that this complete, maximally extended Schwarzschild solution describes an idealized, eternal black hole that has always existed, rather than one that formed at a specific moment from the collapse of a real, physical star and real, astrophysical black holes, which do form from stellar collapse at a specific time, do not actually possess this additional white hole and bridge structure in any way that would be physically accessible or traversable. The bridge connecting the two regions in the idealized eternal solution closes off and pinches shut faster than light could ever travel through it, meaning that even in the idealized mathematical case, no signal or object could actually traverse from one side to the other. The popular science fiction notion of using a black hole's internal structure as a tunnel or shortcut to another part of the universe, while mathematically inspired by this genuine feature of the Schwarzschild geometry, does not represent a physically realistic possibility according to general relativity as currently understood, at least not without introducing additional, highly speculative physical ingredients, such as hypothetical forms of matter with negative energy density, that have never been observed to exist in nature and that may not be physically possible at all. What happens at the singularity itself, the final fate of matter that falls all the way to the center of a black hole, is, as discussed, beyond what general relativity alone can reliably predict. The theory predicts infinite density and infinite spacetime curvature, which essentially every physicist interprets as a sign that the theory has reached the limit of its applicability rather than a literal description of physical reality. What replaces the singularity in a more complete theory, one that successfully incorporates quantum mechanics, remains one of the most actively pursued open questions in theoretical physics. Rotating black holes, which is to say, essentially all real black holes, since stars rotate before they collapse, and that rotation is generally conserved during collapse, introduce additional complexity beyond the simple Schwarzschild solution. The mathematics describing a rotating black hole was worked out by the New Zealand mathematician Roy Kerr in 1963, and the resulting solution, called the Kerr metric, describes a black hole characterized by both mass and angular momentum spin. A rotating black hole drags the surrounding spacetime around with it in a phenomenon called frame dragging, or the Lentz-Thurring effect, predicted by general relativity even for relatively slowly rotating masses like Earth, where the effect is exceedingly tiny but has been measured by extremely precise satellite experiments, and dramatically amplified near a rapidly rotating black hole. Near a rotating black hole, spacetime itself is twisted into a kind of vortex, with the region immediately surrounding the event horizon, called the ergosphere, being an area where it is physically impossible for any object, regardless of its propulsion capability, to remain stationary relative to distant stars. Within the ergosphere, you would be forced to rotate along with the twisting spacetime, whether or not you wanted to, though you could, in principle, still escape back out of the ergosphere, since it lies outside the actual event horizon. The ergosphere has a genuinely remarkable theoretical property. It's possible, in principle, to extract energy from a rotating black hole by exploiting the physics of this region through a process called the Penrose process, proposed by Roger Penrose in 1969. By dropping an object into the ergosphere and having it split into two pieces, with one piece falling into the black hole on a trajectory that actually reduces the black hole's angular momentum and the other piece escaping with more energy than the original object possessed, energy can be extracted from the black hole's rotational energy itself. This isn't a violation of energy conservation. The energy comes at the direct expense of the black hole's spin, gradually slowing its rotation over repeated extractions, but it represents one of the only theoretically known mechanisms by which the energy locked within a black hole could, in principle, be tapped by some sufficiently advanced civilization. A related and astrophysically much more important phenomenon is the Blandford-Znajek process, proposed in 1977, which describes how a rotating black hole's enormous rotational energy can be extracted through interaction with strong magnetic fields threading the ergosphere, a mechanism widely believed to power the extraordinarily energetic jets of particles observed shooting out from many active supermassive black holes at relativistic speeds, sometimes extending for hundreds of thousands of light years beyond their host galaxies. These jets, visible in radio telescope observations of active galactic nuclei, represent some of the most powerful and energetic phenomena in the observable universe, and the rotational energy of the central black hole, tapped through processes like Blandford-Znajek, is the leading explanation for how they're powered. The structure of a rotating black hole is considerably more intricate than the simple, single spherical event horizon of the non-rotating Schwarzschild case. A rotating, or Kerr, black hole actually possesses two distinct horizons, an outer event horizon, beyond which escape is impossible, just as in the non-rotating case, and an inner horizon, located deeper within, whose precise physical significance has been a subject of extensive theoretical debate. Classical general relativity predicts that the inner horizon would be a region of extreme, potentially infinite tidal stretching for any infalling observer, sometimes called a mass inflation singularity, distinct from, and in some models considered even stranger than the central singularity itself. Whether this inner horizon structure survives intact once quantum effects are properly incorporated remains an open theoretical question, and some physicists suspect that quantum corrections would smooth out or fundamentally alter this feature of the classical solution. The shape of the singularity itself also changes for a rotating black hole, rather than the simple point-like singularity of the non-rotating case. The Kerr solution predicts a ring-shaped singularity, a genuinely strange mathematical structure that, intriguingly, an observer could in principle pass through the center of without actually striking the singularity itself. emerging into a mathematically distinct region of the extended space-time where the equations describe negative distances and other features with no clear physical interpretation. As with the Schwarzschild white hole and bridge structure discussed earlier, most physicists regard these exotic extended features of the idealized, eternal Kerr solution as mathematical artifacts of an idealization that doesn't correspond to any realistic black hole formed through actual stellar collapse, rather than as genuine predictions about what would actually be encountered by an observer falling into a real, astrophysical rotating black hole. Spin measurements of real astrophysical black holes have become possible in recent years through detailed analysis of X-ray emission from the innermost regions of accretion disks, and through the gravitational wave signals captured by LIGO and Virgo, which encode information about the spins of the merging black holes in the detailed shape of the detected waveform. These measurements have revealed that many black holes, both stellar mass and supermassive, are spinning extremely rapidly, in some cases close to the theoretical maximum allowed by general relativity, a finding that has significant implications for understanding how these black holes formed and grew over cosmic time. Black holes are not, despite the popular image, cosmic vacuum cleaners that relentlessly suck in everything around them with some kind of special, irresistible force. Gravitationally, a black hole affects objects around it exactly the way any other object of the same mass would. If our sun were somehow instantaneously replaced by a black hole of exactly the same mass, an admittedly extreme and physically implausible scenario, Earth's orbit would not change at all. We would lose the sun's light and heat, with catastrophic consequences for life on Earth. But the orbital mechanics governing our planet's motion around the central mass would remain entirely unaffected because gravity, in both Newtonian and Einsteinian physics, depends on mass and distance, not on whether that mass happens to be compressed into a black hole or spread out as an ordinary star. What makes black holes seem so dramatically destructive in popular imagination, and what genuinely is dramatic and destructive in specific, close-range circumstances, relates to events near the event horizon itself, not to any special long-range gravitational reach. A black hole's gravity follows exactly the same inverse square law as any other mass at any reasonable distance. It's only as you approach extremely close to the event horizon that the effects become genuinely different from what ordinary Newtonian gravity would predict, and only within a relatively small region around the black hole that anything unusual occurs. A useful way to correct the vacuum cleaner myth is to imagine distance. Far from the event horizon, a black hole is simply mass. Replace a star with a black hole of the same mass, and the distant orbits around it do not suddenly collapse. A planet orbiting far away would continue following almost the same path, because the gravitational field at that distance is determined by the total mass inside the orbit, not by whether that mass is spread through a luminous star or compressed behind a horizon. The danger begins only when the distance becomes small enough that the compactness of the black hole matters. A normal star has a surface that stops you long before you can approach the center of its mass. A black hole has no such surface. You can keep falling inward to radii that would be inside any ordinary star, and because gravity grows stronger at smaller distances, the environment becomes extreme. That is the real difference. A black hole does not pull harder from far away because it is a black hole. It allows matter to approach much closer to the same mass than any normal object would. This is why black holes can be both ordinary and extraordinary at the same time. From a distance, they obey gravity like everything else. Up close, they reveal what gravity becomes when mass is compressed beyond all ordinary limits. This doesn't mean black holes are harmless to objects that wander into their vicinity, of course. A star that passes too close to a supermassive black hole can be torn apart by tidal forces in a dramatic and genuinely observable phenomenon called a tidal disruption event. As the star approaches the black hole, the difference in gravitational pull between the near and far sides of the star becomes strong enough to overcome the star's own self-gravity, ripping it apart into a long, glowing stream of stellar debris, roughly half of which falls into the black hole, producing a brilliant, temporary flare of radiation as the infalling material is heated to extreme temperatures, while the other half is flung outward into interstellar space. Astronomers have observed dozens of these tidal disruption events in distant galaxies over the past 2 decades, each one offering a unique opportunity to study the physics of extreme gravitational interactions and to probe the properties of the otherwise invisible black hole responsible. Within our own solar system, there's no remotely realistic scenario in which a black hole poses any danger. The nearest known black hole to Earth, designated Gaia BH1, is located about 1,560 light-years away, far too distant to have any measurable gravitational effect on anything in our solar system, and indeed too distant to be detected by any means other than the careful, precise astrometric measurements of the European Space Agency's Gaia spacecraft, which tracked subtle wobbles in the motion of a visible companion star caused by its gravitational dance with the unseen black hole. Let's spend some time now with what happens when a black hole, rather than sitting quietly, is actively feeding on its surroundings, because the most luminous, most energetic objects in the observable universe are powered not by stars, but by actively accreting supermassive black holes. When a supermassive black hole at a galaxy's center has a sufficient supply of nearby gas to consume, it can become what astronomers call an active galactic nucleus, a region at the center of a galaxy outshining, in some cases, the combined light of every single star in the host galaxy, despite the black hole itself occupying a region of space that, by galactic standards, is vanishingly small. The mechanism powering this extraordinary luminosity is gravitational and frictional, not nuclear. As gas spirals inward through the accretion disk toward the event horizon, the conversion of gravitational potential energy into heat through friction between adjacent layers of infalling material is extraordinarily efficient, far more efficient, in fact, than the nuclear fusion that powers ordinary stars. Accretion onto a black hole can convert roughly 10% of the infalling material's rest mass energy into radiated light, compared to less than 1% for the hydrogen fusion that powers the sun, making black hole accretion one of the most efficient energy-generating processes known anywhere in physics. The most extreme examples of active galactic nuclei are quasars, first identified in the early 1960s as mysterious, star-like points of light with peculiar spectral properties that defied explanation using the physics known at the time. The breakthrough came when astronomers realized that the strange spectral lines observed in these objects were ordinary, well-understood atomic emission lines, but shifted dramatically toward longer, redder wavelengths, a redshift indicating that these objects were not nearby stars at all, but extraordinarily distant galaxies, so far away that the expansion of the universe itself was stretching their light substantially during its journey to Earth. For an object that distant to appear as bright as it did in available telescopes required it to be intrinsically more luminous than entire ordinary galaxies. A puzzle that wasn't satisfactorily resolved until the supermassive black hole accretion model became established in subsequent decades. Quasars are now understood to represent a particular phase, or a particular orientation, within a broader and more unified picture of active galactic nuclei. The same basic underlying physical structure, a supermassive black hole, a surrounding accretion disk, often a thick surrounding torus of dust and gas, and in many cases a pair of energetic jets launched along the black hole's rotation axis can present very differently to an observer depending primarily on the viewing angle and on how much gas is currently being actively fed into the system. Viewed face-on, with a clear line of sight directly into the blazing accretion disk, such an object might appear as a quasar. Viewed edge-on, with the central engine obscured by the surrounding dusty torus, the same fundamental object might instead appear as a different observational category, sometimes called a Seyfert galaxy, where the active nucleus is comparatively much fainter and the host galaxy's own starlight remains visible. This unification scheme, developed substantially through the 1980s and 1990s, has been one of the most successful organizing frameworks in extragalactic astrophysics, even though some details continue to be refined as observations improve. The relativistic jets launched by some active black holes represent among the most powerful, most extreme phenomena known anywhere in the universe. These narrow, tightly collimated streams of charged particles are accelerated to speeds extraordinarily close to the speed of light, in some cases exceeding 99% of light speed, and can extend for hundreds of thousands of light years beyond their host galaxy, vastly larger than the galaxy itself. The exact mechanism by which these jets are launched and collimated into such narrow, stable streams over such enormous distances remains an active area of research, though the leading models, building on the Blandford-Znajek process discussed earlier, involve the black hole's powerful magnetic field, anchored partly in the rotating accretion disk and partly in the black hole's own spin, channeling and accelerating charged particles along the rotation axis in a manner broadly analogous to, though far more powerful than, the magnetic processes that shape solar flares and coronal mass ejections from our own sun. This activity has consequences that extend well beyond the immediate vicinity of the black hole itself. The enormous energy output of an active galactic nucleus, whether channeled through powerful jets, through intense radiation pressure, or through energetic outflowing winds of gas, can heat and disperse the surrounding gas within the host galaxy, suppressing the galaxy's ability to form new stars from that gas. This feedback process, mentioned briefly earlier, is now considered an essential ingredient in models of galaxy formation and evolution, helping to explain several otherwise puzzling observations. Why the most massive galaxies in the universe contain comparatively less cold gas and form fewer new stars than would otherwise be expected, why there appears to be a natural upper limit to how large galaxies typically grow, and why the mass of a galaxy's central black hole correlates so closely with properties of its surrounding bulge of stars, as though the two were grown together through some kind of self-regulating feedback loop, with the black hole's energetic output periodically throttling back the very gas supply that would otherwise feed both further star formation and further black hole growth. In 1974, Stephen Hawking applied the principles of quantum field theory, the framework describing how particle fields behave, including the unsettling but well-established phenomenon of virtual particle pairs constantly popping in and out of existence throughout empty space, even in a vacuum, to the curved space-time immediately surrounding a black hole's event horizon. His calculation revealed something startling. Black holes are not, in fact, perfectly black. They should, according to quantum mechanics applied near the event horizon, emit a faint thermal radiation, now universally known as Hawking radiation. The intuitive, though admittedly imprecise, explanation often given is that pairs of virtual particles, a particle and its corresponding antiparticle, are constantly being created and annihilated throughout space due to quantum uncertainty. Near the event horizon of a black hole, it's possible for one particle of such a pair to fall into the black hole while its partner escapes to infinity, becoming a real, detectable particle rather than a fleeting virtual one. From the perspective of a distant observer, the black hole appears to be emitting particles, radiating energy, even though, classically, nothing should be able to escape from within the event horizon at all. This radiation comes at a direct cost to the black hole. By energy conservation, the particle that falls into the black hole must carry negative energy relative to the external observer's frame, which means the black hole's total mass energy very gradually decreases over time. Black holes, according to this theory, are slowly evaporating, losing mass at a rate that depends inversely on their mass, meaning, counterintuitively, that smaller black holes evaporate much faster than larger ones, and the rate accelerates dramatically as the black hole shrinks. For any astrophysically realistic black hole, stellar mass, or larger, this evaporation process is almost inconceivably slow. The temperature of Hawking radiation for a black hole of solar mass is calculated to be only about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that permeates all of space at a temperature of about 2.7 degrees above absolute zero, meaning that any astrophysical black hole is currently absorbing far more energy from this background radiation than it's losing through Hawking radiation, and will continue doing so for an extraordinarily long time into the future, as the universe itself continues to cool through its ongoing expansion. The calculated evaporation timescale for a solar mass black hole is approximately 10 to the power of 67 years, a number so vastly larger than the current age of the universe, about 13.8 billion years, that it defies any meaningful intuitive comparison. Only after the universe has cooled enough, in the unimaginably distant future, will black holes begin to lose mass to Hawking radiation faster than they gain it from the background radiation, beginning their slow, genuine evaporation, which would only reach a dramatic, final, explosive conclusion after a timescale that represents one of the longest duration physical processes contemplated in any serious scientific theory. Despite never having been directly observed, Hawking radiation is taken extremely seriously by the physics community because it emerges from combining two of the best-tested theories in all of physics, general relativity and quantum field theory, in a regime where both should, in principle, apply. Its theoretical implications extend well beyond simple black hole evaporation, touching on one of the most contentious unresolved puzzles in modern theoretical physics: the black hole information paradox. There is a useful caution here. The common virtual particle picture of Hawking radiation is a helpful mental image, but it is not the full calculation. In the actual physics, Hawking radiation emerges from the way quantum fields behave in curved spacetime, and from the difference between how particles are defined near the horizon and how they are defined far away. The simplified story gives the right intuition that the black hole loses energy, but the mathematics is deeper and less mechanical than a pair of particles literally appearing at the horizon like tiny objects in ordinary space. That distinction matters because black holes are often discussed with images that sound simple but conceal very subtle physics. The event horizon is not a surface. The singularity is not a normal object. Hawking radiation is not ordinary thermal glow from a material body. A black hole forces us to use language that was built for everyday experience to describe conditions where everyday experience has almost no authority. The information paradox arises from an apparent, deeply troubling conflict between general relativity and quantum mechanics regarding what happens to information that falls into a black hole. One of the most fundamental principles of quantum mechanics is that information, in a technical sense, the complete physical description of a system's quantum state, cannot simply be destroyed. Physical processes can transform information, scramble it, render it practically impossible to reconstruct, but in principle, Given perfect knowledge of a system's initial state and the laws governing its evolution, you should always be able to determine, at least mathematically, the system's state at any later time, and vice versa. This principle, called unitarity, is foundational to the entire framework of quantum theory. But Hawking's original calculation of black hole radiation suggested something that appeared to directly violate this principle. The radiation a black hole emits, according to his original analysis, should be perfectly thermal, meaning it carries no information whatsoever about what fell into the black hole to begin with. Drop a book into a black hole, or a star, or a person, or anything else, and according to this picture, the black hole would eventually evaporate away entirely through Hawking radiation, leaving behind nothing but featureless thermal radiation, with absolutely no trace of the specific information that characterized whatever fell in. The information, it seemed, would simply be destroyed, erased from the universe entirely once the black hole had fully evaporated, a direct and apparently irreconcilable contradiction with the unitarity principle that underlies all of quantum mechanics. This apparent contradiction, which Hawking himself first highlighted in the 1970s, became one of the most persistent and actively debated puzzles in theoretical physics for nearly 5 decades, drawing in some of the most prominent physicists of the era and generating an enormous body of theoretical work attempting to resolve it. Various proposed resolutions have included the idea that information is somehow encoded in extremely subtle correlations within the supposedly thermal Hawking radiation itself, which would require modifying or refining the original calculation. The idea that information is stored on the event horizon itself in some kind of holographic encoding, related to a broader and very influential idea in theoretical physics called the holographic principle. The idea that black holes don't actually have genuine singularities or true event horizons in the way classical general relativity predicts, but instead some more exotic structure, sometimes called a fuzzball in certain string theory approaches, that would naturally allow information to be preserved and gradually leak back out. And even Hawking's own eventual partial concession in 2004, in which he conceded a long-standing bet with physicist John Preskill, suggesting that information is indeed preserved, though precisely how remained unclear even to him. A significant theoretical breakthrough came in the 2010s and culminated more substantially around 2019 and 2020 through work involving what are called quantum extremal surfaces and a refined mathematical technique often referred to as the island formula, developed by several groups of theoretical physicists working at the intersection of quantum gravity, string theory, and information theory. This body of work, building on decades of accumulated theoretical insight, suggests a path by which information could indeed gradually be encoded in the correlations of Hawking radiation in a way consistent with unitarity, potentially resolving the paradox, at least within certain simplified theoretical models that are more mathematically tractable than the full complexity of a real, four-dimensional, astrophysical black hole. It's important to be clear about where the scientific consensus genuinely stands on this question. While significant theoretical progress has been made, and many physicists working in quantum gravity now believe that information is, in some sense, ultimately preserved during black hole evaporation, a complete, fully rigorous, and universally agreed upon resolution of the information paradox, one that applies cleanly to realistic, four-dimensional black holes rather than simplified theoretical toy models, remains an active and unresolved area of research. The black hole information paradox stands as one of the genuinely open frontiers where our two best fundamental theories of physics, general relativity and quantum mechanics, have not yet been successfully and completely reconciled. It's worth dwelling for a moment on why this particular puzzle has commanded so much sustained attention from theoretical physicists over the past 5 decades. because the stakes involved extend well beyond simply understanding black holes themselves. The information paradox sits precisely at the intersection of general relativity and quantum mechanics, the two great pillars of modern physics, each spectacularly successful within its own domain, yet notoriously difficult to reconcile into a single, unified theoretical framework. General relativity describes gravity and the large-scale structure of space-time with extraordinary precision, confirmed through tests ranging from the precession of Mercury's orbit to the direct detection of gravitational waves. Quantum mechanics describes the behavior of matter and energy at the smallest scales with equally extraordinary precision, confirmed through tests ranging from the structure of atoms to the operation of the electronic devices that, in some form, are very likely involved in however you're listening to this right now. But the two theories, as currently formulated, simply don't fit together cleanly. Attempting to apply the mathematical machinery of quantum mechanics directly to the gravitational field, in the most straightforward way physicists initially tried, produces nonsensical, infinite results that cannot be meaningfully interpreted. Black holes, precisely because they combine both extremely strong gravitational fields and, particularly in their final stages of evaporation, conditions where quantum effects become significant, represent one of the very few places in physics where this tension between our two best theories becomes scientifically unavoidable and experimentally, or at least theoretically, testable in a meaningful sense. If physicists can fully and rigorously work out exactly what happens to information that falls into a black hole, consistently with both general relativity's predictions about the event horizon and quantum mechanics' insistence that information cannot simply be destroyed, the resulting theoretical framework would represent a genuine and substantial step toward the long-sought, more complete theory of quantum gravity that has eluded physicists since shortly after quantum mechanics itself was first developed in the 1920s. This is part of why the information paradox, despite initially appearing to be a somewhat narrow, technical puzzle specifically about black hole physics, has come to occupy such a central position in contemporary theoretical physics, drawing in researchers working across string theory, loop quantum gravity, and numerous other approaches to quantum gravity, each bringing different mathematical tools and conceptual frameworks to bear on what remains, even after decades of sustained effort, a genuinely unresolved scientific puzzle. Let's turn now to one of the most genuinely fascinating mysteries in modern astrophysics: the puzzle of how supermassive black holes manage to grow as large as they do, particularly in the early universe. The standard, intuitively appealing picture of supermassive black hole growth involves a gradual process. A stellar mass black hole forms from the collapse of an early, massive star. It grows over time by accreting surrounding gas and dust, and by merging with other black holes during galactic collisions, and over billions of years, through this slow, incremental process, it eventually grows into the millions or even billions of solar masses observed at the centers of large galaxies today. This picture works reasonably well for explaining supermassive black holes observed in the relatively nearby, and therefore relatively recent, universe. But it runs into a serious and increasingly well-documented problem when applied to the most distant, and therefore earliest, quasars that astronomers have discovered. A quasar is an extraordinarily luminous active galactic nucleus, powered by a supermassive black hole rapidly accreting matter, generating so much energy through the resulting friction and radiation that it can outshine the combined light of every star in its host galaxy, often by a significant margin, making quasars detectable across truly vast cosmic distances, even from the very early universe. Beginning in the early 2000s and accelerating dramatically with more recent, more powerful telescope surveys, astronomers have discovered quasars at extraordinary distances, corresponding to a universe that was less than 1 billion years old, meaning we are observing these objects as they existed when the universe itself was less than 7% of its current age. The problem is one of timing and growth rate. Several of these extremely distant quasars host black holes with estimated masses of 1 billion solar masses or more, already fully formed and actively accreting within less than 1 billion years after the Big Bang. Given the known physical limits on how quickly a black hole can grow by accreting surrounding matter, a theoretical limit called the Eddington limit, which arises because the radiation pressure generated by infalling, heated material eventually pushes back against further infall, self-regulating the maximum sustainable accretion rate, it becomes extremely difficult, under standard assumptions, for a black hole that started from an ordinary stellar mass seed, formed from the collapse of an early star weighing perhaps 100 times the mass of our Sun, to grow to 1 billion solar masses within such a comparatively short cosmic time frame, even accounting for the somewhat higher accretion rates and more abundant surrounding gas that characterize the considerably denser early universe. This persistent difficulty has led theoretical astrophysicists to propose several alternative formation mechanisms for the initial seed black holes that would go on to grow into these earliest observed supermassive giants. One prominent and increasingly favored hypothesis involves what are called direct collapse black holes, the idea that under specific, relatively rare conditions in the early universe, an enormous, pristine cloud of primordial gas, lacking the heavy elements that would normally allow it to cool efficiently and fragment into many individual stars, could instead collapse directly and rapidly into a single, already very massive black hole, potentially tens of thousands of times the mass of our Sun, entirely bypassing the conventional intermediate stage of forming an ordinary star first. Such a vastly more massive starting seed would have a substantial head start in the subsequent race to grow into 1 billion solar mass black hole within the available cosmic time. Another, related hypothesis involves the formation of so-called quasi-stars, extraordinarily massive, unstable, transient objects in which a black hole forms and begins growing within the core of a still collapsing protostellar cloud, with the surrounding cloud's remaining outer layers acting almost like an enormous stellar envelope, continuing to rapidly and efficiently feed material directly into the central black hole even as the structure as a whole remains, for a relatively brief period, recognizably star-like in its outward appearance and behavior. A third proposed pathway involves runaway stellar collisions and mergers within extraordinarily dense, young star clusters in the early universe. In sufficiently crowded stellar environments, far denser than any star cluster found in the present day, more dynamically settled universe, massive stars could, in principle, collide and merge with one another repeatedly over a relatively short period, building up a single extraordinarily massive object far exceeding the mass of any star that could form through ordinary, gradual accretion from a collapsing gas cloud alone. Such a runaway merger object, sufficiently massive, would itself be prone to direct collapse into a substantial black hole seed, potentially providing yet another viable pathway toward the early, rapid formation of unusually massive seeds capable of growing into the billion solar mass quasars observed in the very early universe. Distinguishing observationally between these competing seed formation scenarios, direct collapse, quasi-stars, and runaway stellar merger pathways, remains genuinely difficult with current instrumentation, since each predicts somewhat different but still broadly similar present-day observational signatures, particularly once a few 100 million years have passed, and the resulting black hole has already grown substantially through subsequent accretion, gradually erasing some of the more specific, distinguishing details of its original formation pathway. Some theorists have proposed that gravitational wave observatories of the future, particularly the space-based LISA mission currently in development by the European Space Agency, specifically designed to detect lower-frequency gravitational waves than ground-based detectors like LIGO can access, might be capable of directly detecting the mergers of these earliest, most massive black hole seeds, potentially providing a much more direct observational window into this currently quite uncertain and actively debated period of cosmic history than electromagnetic observations alone can offer. The James Webb Space Telescope, which began science operations in 2022, has been specifically designed with the sensitivity and infrared capability needed to detect light from extremely distant, early universe galaxies and quasars, and its observations in just the past few years have already substantially extended the population of known early, massive black holes, while also revealing several unexpected and genuinely puzzling features, including supermassive black holes that appear, surprisingly, to be unusually overmassive relative to their host galaxies when compared to the well-established relationship observed in the more nearby, present-day universe, where a galaxy's central black hole mass and its host galaxy's overall stellar mass are known to be closely correlated. This and other recent observations are actively reshaping theoretical models of how the very first generation of supermassive black holes came to exist, and the question remains genuinely, actively unresolved, representing one of the most dynamic and rapidly evolving frontiers in contemporary observational astrophysics. It's worth taking some time to properly understand Sagittarius A star, the supermassive black hole at the very center of our own Milky Way galaxy, since it represents both the closest supermassive black hole to Earth and one of the most thoroughly, precisely studied black holes anywhere in the observable universe. Sagittarius A star. The asterisk is conventionally pronounced a star, and the unusual naming reflects its original discovery and designation as a particularly compact, particularly excited radio source within the broader, much larger radio source called Sagittarius A, sits at a distance of approximately 26,000 light-years from Earth, located in the direction of the constellation Sagittarius, though it remains entirely invisible to direct optical observation due to the enormous quantities of intervening interstellar gas and dust that lie along essentially any line of sight toward the crowded, densely packed galactic center. As discussed earlier, the existence and precise mass of Sagittarius A star were first convincingly established through more than 2 decades of extraordinarily careful, patient tracking of the orbital motions of individual stars in its immediate vicinity, work that ultimately earned Reinhard Genzel and Andrea Ghez a share of the 2020 Nobel Prize in Physics. These detailed orbital measurements indicate a central mass of approximately 4 million times that of our Sun, concentrated within a remarkably small region of space, a result that, combined with the complete absence of any directly visible counterpart bright enough to explain such an enormous mass through any other known astrophysical process, leaves a supermassive black hole as overwhelmingly the only viable explanation consistent with all available evidence. In May 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, capturing its characteristic dark central shadow, surrounded by a bright, glowing ring of superheated material in its immediate surroundings, the second such direct black hole image ever produced. Following the landmark 2019 image of the substantially more massive black hole at the center of the considerably more distant galaxy, M87. Producing the Sagittarius A star image required overcoming substantial additional technical challenges beyond those already encountered with M87. Because Sagittarius A star is dramatically less massive than M87's central black hole, material in its immediate vicinity orbits and varies on much shorter timescales, changing noticeably within mere minutes rather than over days, requiring the development of sophisticated computational and statistical techniques specifically designed to produce a single, stable, scientifically reliable image from data collected over an extended observational period during which the source itself was continuously and rapidly changing. The quietness of Sagittarius A star is itself scientifically useful, because it is not buried beneath the glare of a powerful quasar. Astronomers can track individual stars around it with unusual precision. Their orbits turn the center of the Milky Way into a natural gravitational laboratory. Every close pass of a star like S2 tests how well general relativity works in a region where gravity is far stronger than anything available in the solar system. During S2's close approach in 2018, astronomers measured a gravitational redshift. The star's light was stretched to longer wavelengths by the intense gravity near Sagittarius A star, exactly as general relativity predicts. Subsequent observations have also traced the star's orbital precession, another relativistic effect. These measurements do not require falling into the black hole or seeing the event horizon directly. They use the motion of ordinary stars as test particles moving through curved spacetime. That is one of the recurring themes of black hole astronomy. The black hole itself may be dark, but it writes its presence into everything around it. It bends light. It accelerates gas. It pulls stars into tight orbits. It launches jets. It sends gravitational waves across the universe when it merges with another black hole. We know black holes not because they shine, but because the universe around them cannot move as it does unless they are there. Sagittarius A star is, by astrophysical standards, a remarkably quiet and relatively unremarkable supermassive black hole in terms of its current overall activity level. Unlike many other supermassive black holes observed throughout the universe, particularly those powering the extraordinarily luminous quasars discussed earlier, Sagittarius A star is not currently consuming and accreting matter at anywhere near its theoretical maximum possible rate. The total luminosity generated by Sagittarius A star's comparatively modest, low-level accretion activity is many orders of magnitude lower than what would be theoretically possible for a black hole of its substantial mass. A phenomenon astronomers generally attribute to the surrounding environment at the galactic center simply not currently providing very much readily available gas and dust for the black hole to actively consume and accrete at any given time. This relative quiescence has not always characterized Sagittarius A star's history, however. Several independent lines of observational evidence, including distinctive, large-scale structures sometimes referred to as the Fermi bubbles, enormous gamma-ray emitting lobes of material extending tens of thousands of light-years above and below the plane of our galaxy, first clearly identified in 2010, strongly suggest that Sagittarius A star experienced one or possibly several significantly more energetic, more active outburst episodes within roughly the past several million years. A relatively brief and recent period by the standards of cosmic and galactic time, during which considerably more gas was being actively consumed and converted into energy, generating much more substantial high-energy radiation and powerful outflows than what we currently observe. Sagittarius A star will, in the very distant astronomical future, eventually merge with the supermassive black hole currently residing at the center of the neighboring Andromeda galaxy, as the two galaxies themselves are projected to gradually collide and merge together over a period of several billion years, beginning roughly 4 billion years from now. Such galactic mergers are now understood to be a primary, well-established mechanism through which supermassive black holes continue to grow substantially larger over cosmic time, and the eventual merger of our own galaxy's central black hole with Andromeda's will itself generate a powerful, characteristic burst of gravitational waves, though one with a far longer wavelength, and therefore requiring detection methods very different from the current generation of ground-based gravitational wave. Observatories like LIGO, which are specifically designed and optimized to detect the comparatively much higher frequency gravitational waves produced by considerably smaller stellar mass black hole mergers. There are several genuinely significant, currently unresolved questions about black holes that remain active areas of vigorous ongoing research, and it's worth taking the time to properly acknowledge them rather than presenting black hole physics as a more fully settled, complete subject than it actually, honestly is. The black hole information paradox, discussed earlier, remains incompletely resolved despite the substantial recent theoretical progress made through work involving quantum extremal surfaces and the so-called island formula. A complete, fully general resolution that applies cleanly and rigorously to realistic, astrophysically relevant black holes, rather than to deliberately simplified theoretical toy models constructed specifically to make the underlying mathematics more tractable, has not yet been definitively achieved, and substantial theoretical work continues across multiple independent research programs attempting to fully close this conceptual gap. The true nature of the singularity at a black hole's center remains entirely unknown. General relativity confidently predicts infinite density and correspondingly infinite spacetime curvature at this central point. But virtually all physicists agree this almost certainly indicates the genuine breakdown of general relativity's applicability in that specific extreme regime, rather than representing any kind of literal, physically accurate description of what is actually present there. A complete and successful theory of quantum gravity, one that would properly and consistently describe physics at the smallest possible length scales, while gravity itself remains extraordinarily strong, would very likely replace the troublesome singularity with something genuinely different, though precisely what that replacement structure might actually look like remains entirely unknown and is the subject of multiple, often substantially competing theoretical approaches, including various forms of string theory, loop quantum gravity, and several other less mainstream, but still seriously considered theoretical frameworks. The precise formation mechanism responsible for the earliest, most massive supermassive black holes observed in the early universe remains an actively and intensely debated open question, as discussed in some detail above, with direct collapse black holes, quasi-stars, and various other proposed alternative seed formation mechanisms, all still under serious, ongoing theoretical and observational consideration and investigation by different research groups around the world. Whether or not primordial black holes genuinely exist in significant numbers, and if so, whether they might constitute some meaningful fraction of the universe's mysterious dark matter, remains scientifically unresolved. Current observational constraints have successfully ruled out primordial black holes as the dominant overall component of dark matter across most of the theoretically plausible range of possible masses. But certain narrower mass windows remain observationally unconstrained and continue to be actively investigated through a variety of different and complementary observational techniques. The detailed physics governing precisely how matter actually behaves while falling through a black hole's event horizon, beyond the relatively simple classical picture provided by general relativity alone, particularly once meaningful quantum mechanical effects are properly taken into account, remains incompletely understood. Various recent and ongoing theoretical proposals, including black hole firewalls, a controversial hypothesis suggesting that an infalling observer might actually encounter a dramatic, destructive wall of high-energy particles precisely at the event horizon, rather than experiencing the gentle, locally unremarkable, seemingly uneventful crossing that standard general relativity alone would predict, and various competing fuzzball models from string theory represent serious and actively pursued attempts to address this specific lingering problem, but no clear scientific consensus has yet been firmly reached. These open, unresolved questions are not, in any sense, indications of some fundamental failure or weakness of modern black hole physics. Quite the opposite. They represent the genuine, productive, actively advancing frontier of an extraordinarily rich and rapidly developing field, one in which dramatic and significant new observational and theoretical progress has been made within just the past decade, from the first ever gravitational wave detection in 2015 to the first direct images of black hole event horizons in 2019 and 2022, to substantial ongoing theoretical breakthroughs concerning the information paradox. The honest, complete answer to many of the very deepest questions about black holes remains genuinely, scientifically, we don't yet fully know. And the sustained, dedicated effort to eventually find out represents some of the very best and most ambitious work currently being done anywhere in contemporary physics. There is something worth sitting with, before we close, about what black holes represent within the broader context of the universe's history and its eventual long-term future. Black holes are not simply destructive cosmic anomalies, despite their fearsome popular reputation. They appear to play a genuinely active and important constructive role in regulating and shaping galactic evolution. The supermassive black hole residing at the center of a typical large galaxy, through the energy and powerful outflows generated periodically during its more active accretion phases, can directly influence and even substantially limit the rate at which surrounding gas is able to cool and collapse to form entirely new generations of stars throughout the host galaxy, a regulatory process astronomers refer to as feedback, which appears to be genuinely essential for properly explaining several otherwise puzzling observed properties of galaxies, including why the very largest galaxies in the universe don't simply continue accumulating gas and forming new stars indefinitely, but instead reach a relatively stable, self-regulated equilibrium over sufficiently long cosmic timescales. There is one more observational frontier that belongs in this story: the sound a black hole makes in spacetime after it forms. When two black holes merge, the final object does not become perfectly settled instantly. It rings, not with sound waves in air, of course, but with vibrations in the curvature of spacetime itself. These vibrations are called quasi-normal modes, and they appear in the final part of a gravitational wave signal, the ring down. The frequencies and decay rates of those modes are predicted by general relativity to depend only on the final black hole's mass and spin. That makes ring down one of the cleanest tests of the black hole idea. If the final object is really a Kerr black hole, the rotating black hole solution of general relativity, then all of its ringing modes should fit the pattern allowed by that mass and spin. If future detectors observe a strong enough signal with enough precision to measure several modes clearly, physicists can test whether the final object behaves exactly like the black holes predicted by Einstein's theory, or whether something more exotic is hiding at the horizon scale. This is one reason the future of black hole astronomy is not only about seeing farther. It is about listening more precisely. Ground-based detectors are improving. New detectors are being planned. Space-based gravitational wave observatories such as LISA are expected to detect lower frequency waves from much larger black hole systems, including mergers of massive black holes in the early universe. Those signals could open a new view of how the first supermassive black holes formed and grew. In the truly distant future of the universe, looking many trillions of years ahead, vastly longer than even the current age of the universe itself, black holes are projected to become, in a very real and literal sense, among the very last interesting, complex objects remaining in an otherwise increasingly cold, dark, and dilute cosmos. As the universe's continuing expansion gradually but relentlessly disperses matter into ever greater isolation, as existing stars individually exhaust their available nuclear fuel, and no genuinely new stars can continue forming once the available supply of fresh hydrogen gas is eventually fully exhausted, and as stellar remnants very gradually settle through extraordinarily slow processes into the deep gravitational wells of the supermassive black holes residing at galactic centers. Black holes themselves are expected to persist as some of the very last remaining significant structures, slowly and patiently evaporating away through the Hawking radiation process discussed earlier, over genuinely staggering timescales currently estimated to be on the order of 10 to the power of 100 years for the most massive black holes. This far future scenario, sometimes evocatively referred to as the black hole era, in various theoretical cosmological models charting the universe's eventual long-term fate, represents an almost unimaginably distant and remote period, so far removed from the present moment that the number of years separating us from it dwarfs, by an inconceivably vast margin, the current age of the universe itself, which is only 13.8 billion years old. And yet it remains a legitimate and scientifically serious subject of theoretical investigation, illustrating in a genuinely striking way just how fundamental and persistent black holes are to our overall understanding of how the universe, considered across truly cosmic timescales, both evolves and ultimately, eventually, comes to an end. There is, finally, something quietly remarkable in simply considering that all of this, the event horizons, the singularities, the Hawking radiation, the merging black holes whose gravitational ripples have crossed unimaginable cosmic distances to be detected here on Earth by instruments of extraordinary engineering precision, exists because massive stars, scattered throughout galaxies across the observable universe, eventually exhaust their nuclear fuel and collapse under the relentless, patient pull of their own gravity. The black hole at the center of our own galaxy has been there, quietly, patiently, for billions of years, slowly growing through the accretion of surrounding gas and through periodic mergers with other black holes, while stars trace their graceful, precise orbits around it, while the galaxy itself slowly rotates, while our own solar system completes its own roughly 230 million year orbital journey around that distant galactic center. Sagittarius A star will still be there, essentially unchanged in any meaningful way, long after every human being currently alive has lived out their life. It will still be there when the sun, several billion years from now, eventually exhausts its own nuclear fuel and expands into a red giant. It will still be there, almost certainly continuing to grow larger through accretion and through the eventual merger with Andromeda's own central black hole, for a length of time that fundamentally and genuinely exceeds any meaningful human capacity for direct intuition or comprehension. There is no need to fully resolve or completely understand any of this tonight. The deepest mysteries of black hole physics, what genuinely happens at the singularity, how information is ultimately preserved during evaporation, how the very first generation of supermassive black holes managed to grow so large so quickly in the early universe, remain unresolved even by the physicists who have devoted their entire careers to studying these extraordinary objects in tremendous mathematical and observational detail. These are not simple puzzles awaiting some quick or easy solution. They represent the genuine, current edge of human understanding, the place where our very best and most successful theories, in attempting to fully describe black holes, eventually run out of clear, confident answers and openly admit, with appropriate scientific honesty, the genuine limits of present-day human knowledge. That, in itself, feels like a fitting note to rest on. The universe contains regions definitively proven to be real and yet still only partially understood, where our most successful and well-tested theories quietly admit, with appropriate humility, that they don't yet have a complete and satisfying answer. There is something genuinely calming, rather than unsettling, in that honest admission. The world remains larger, deeper, and more genuinely mysterious than any single, even very good, theory has yet managed to fully capture, and there is more here, patiently waiting to be discovered. Sagittarius A star continues turning, slowly and invisibly, at the heart of our galaxy, 26,000 light-years from where you are right now. The light from the stars precisely orbiting it left those stars years or even decades ago, only now finally arriving at our telescopes here on Earth. The gravitational waves detected by LIGO from black hole mergers occurring more than 1 billion light-years away crossed unimaginable cosmic distances, traveling since long before humans existed and long before any civilization could have built an instrument capable of measuring them, only finally washing past Earth within the past several years. All of this is happening quietly and continuously, whether or not anyone happens to be paying close attention. Black holes are not simply holes in space. They are the end states of stars, the engines of quasars, the anchors of galaxies, the sources of gravitational waves, and the places where our understanding of gravity and quantum mechanics still fails to become one complete picture. They are real, observed, measured, imaged, and still not fully understood. And that is the strongest way to leave them. Not as monsters, not as empty darkness, but as the deepest test objects the universe has given us. Good night.